For our next fireside chat on accelerating fusion R&D, please welcome Sir Steve Cowley, Director of the Princeton Plasma Physics Laboratory, and Scott Parent, Vice President and Field CTO at Ansys. This conversation will be moderated by JP Allain, Associate Director of the Department of Energy Fusion Energy Sciences Program.
All right. Is the mic on? All right. Good morning, everybody. Great to be here with all of you. Jean-Paul Allain, Fusion Energy Sciences and DOE. It's an exciting time for both AI and fusion, and so it's so appropriate that we're gathered here to talk about the impact that AI has, not just in fusion energy in general, but in particular also in ways that AI as an enabling tool can accelerate or help accelerate our way to get fusion on the grid. And so this morning, of course, I'm joined by two good friends, Sir Steve Cowley from Princeton Plasma Physics Lab, the director there, and also a member of the commission, as you've heard, of the recently published report on Fusion Forward. And so, Steve's great to have you here. And another good friend, Scott Parent, who's a VP and the field officer of technology in Ansys. Scott and I have known each other for a while, and lots of great stuff that's going on in Ansys. We'll get into that in a little bit. But Steve, I wanted to just chat with you a little bit about, we've been talking a lot about R&D and the needs and the gaps that are there for fusion. And a lot of the history, in fact, in our program has very much looked at the ability for us to really take advantage and leverage our understanding, knowledge developed from a lot of our, of the research done in the national labs, of course, Princeton included. What are some of the aspects, do you think, Steve, with respect to AI now, that are coming in and really providing an additional tool, let's say, on our quest to realize fusion? What are some of those aspects, Steve, that you see there, and how are you seeing that convergence between AI and fusion energy working out?
Well, so, we've had AI in the fusion research environment really since 1989, when in fact a colleague of mine, Chris Bishop, wrote the control system for the Compass Tokamak, right, in the UK, back in 1989. And since that time, we've been using AI tools for the control. In the last 10 years, groups at General Atomics and at Princeton, Egerman Coleman at Princeton, have been using it to control the system. And we see this on NIF too. But I think that there's something about fusion that's going to benefit from AI more than pretty much any other technology. It's because it's a very, very complex system that we're trying to put together. And if we want to compete in this race, we're going to have to use AI to optimize the system. And we've only scratched the surface of that at this time. We're very lucky that the Department of Energy's program has developed an amazing predictive capability. The exascale computing that we now have, we can calculate roughly and sometimes precisely what happens inside these machines. We've got to integrate that together with AI, and we've got to use that to optimize the future. That will shorten the time to fusion, that will reduce the cost of development, and it will optimize the future device. That's the big challenge that we're facing right now.
Yeah, absolutely. No, couldn't agree more. And Scott, of course, with the leading simulation company like Ansys, you've seen, in fact, in other industries such as automotive and aerospace, the impact that these digital tools can have, for example, in accelerating design, accelerating advances in the research and development, let's say, of a particular technology. Scott, how do you see, for example, Ansys playing a role and also seeing this convergence of these advanced digital tools with fusion and fusion energy?
Yeah, sure. Thanks, JP. It's great being here. I think a couple of things. One, to Sir Stephen's point here, we have we have years of computational effort that's gone into AI. And computational physics and computational chemistry play very, very well. They're another version of computer science and computational science that play very, very well together. If we think of engineering organizations, and this is really where we move from just R&D to thinking ahead to the engineering problem, the manufacturing operational problems, having these digital assets that we've created in R&D to test scenarios and to do sophisticated system, subsystem, and component level analysis, we can then package those up and get secondary value through manufacturing sensitivity. Think about what the folks are trying to do here in Massachusetts with such a scale of spark and the manufacturing challenges and the sensitivities of those challenges in terms of output and performance. If we wrap all that up into a new, if you would, mantra for engineering, this idea of digital engineering, where we take specifications, whether it's a hypersonic system or whether it's a satellite or an automobile, and we flow that down through these models of models and systems of systems, we get to do just what Stephen talked about in terms of optimization. We can do that in R&D, and then do it again in manufacturing for sensitivities around materials, sensitivities around construction complexities. Look at the stellar design and the complexities of that, which are derived through computational analysis. AI layers in very well on top of all of that. And I think it allows us to go faster in those versions and scenarios we want to test. And it does the same thing when we get out into operations and we have things that are time dependent, like fouling or wear or reliability that we want to study. So I think it's exciting. It's an exciting time, as Stephen mentioned, but it's also an exciting opportunity to layer these technologies to advanced pace that we haven't seen before.
Yeah, no, excellent, Scott.
I think, it's going to be very important to address this problem. We can't just outspend China to get fusion first.
Right.
We've got to be smarter, right? And part of that being smarter is to lever the important tools that are around right now. And those, AI is the tool here. We can calculate a lot of these things, but it takes us a long time. Mm-hmm. And when we have AI, we can reduce that time scale so that we can start optimizing the space in which we want to go into there, and it becomes a digital twin of the future fusion reactor. Then all the blind alleys of development get shorter, right? All the routes to fusion get easier. The U.S. has a lead in this. We should keep that lead.
Yeah, absolutely agreed, Stephen. And I think one aspect about AI and as an enabling tool that we don't often talk about is the fact that AI needs data, and data, of course, in terms of being able to acquire it, inherently necessitates the metrology, right? The diagnostic systems that need to, in fact, acquire that data. And also, of course, the prototypic systems and the environments. And I don't know, Steve, maybe you can expand a little bit. Again, we've seen Princeton, other national labs also take a lead and figure it out how to acquire that data for fusion. I mean, fusion energy and its development will rely quite a bit, and the use of AI, frankly, on well-curated, well-defined data that we need. Could you maybe expand a little bit how the laboratory is thinking about this and how you guys are thinking about it from a broad term in terms of supporting fusion energy development?
Yeah, at Princeton, we're about to turn on, in 2026, the world's most powerful spherical tokamak, NSTXU. Right? This is an experiment that all around the world people want the data. There are 5 private companies who will be very interested in that data. But data now is different than it used to be. We used to acquire data and you'd look it up on the computer or whatever. Now that data has to be fed into a system. That system has to train an AI, and that AI has to be the thing that's going to allow us to make the next step forward. And so we are doing this, and we're doing it with General Atomics in San Diego, and we're doing it with a worldwide program to try and restructure the way we use experimental data and the simulations of those data and put it all together in a system that allows us to then develop the digital twin of a future fusion reactor.
Yeah, maybe just to comment on that,
please, Scott. Yep.
I think data in manufacturing and in operation, MRP, ERP systems, people have been spending millions and millions of dollars, billions of dollars over the last few decades to manage what am I going to do with my operations, how am I going to manufacture my products. Then we had something called product life management, PLM systems, that manage bills of materials and revision controls on those bills of materials to get sourcing and supply chain, managing into manufacturing. I think to Stephen's point, the next frontier is going to be what we call simulation process data management, but it's not just simulation data. It's taking simulation data and fusing it, no pun intended, with experimental data from the labs. And this bit of being competitive with China, if we've got decades, like General Atomics, decades and decades of data that we can feed into simulated models, we fuse those, become increasingly accurate, and then feed those to teach our AIs, and we get synthetic then opportunity to be disruptive, we now have very, very sophisticated models running very, very quickly. And ultimately, that's fused from the data that we've collected. But that curated frontier of data management and revision control on what did I teach, how did I teach this model from AI, what did I use, where did that data come from, was it synthetic, merged with experimental data? That's going to be a critical next level of investment, not just in R&D, but to feed then our PLM systems, our ERP, our MRP systems. And that's going to be a connected capability that's going to speed up the manufacturing and deployment of this technology as well.
Yeah, fantastic. And I think also, we're watching, as we speak here, this tremendous investment from the private sector. This was discussed earlier by the Secretary. Steve, how do you see, for example, this convergence now of both, the activities in industry, of course, our natural labs complex, academia, all working together towards supporting fusion? What are your thoughts in terms of that, that bridge that we're trying to build with the private sector, and also the role that Princeton could play in that, in that overall, let's say, ecosystem between these two sectors?
So we're doing a lot of work with the private companies, but one of the key things we do for them is do simulations.
Right.
We have the big codes, and we have the access, and we have the people who know how to run them and do that. And increasingly, those simulations are being shortcut by using AI surrogate models. This is the way they solved the AlphaFold problem for protein folding and got the Nobel Prize in chemistry, right? Which is, you can solve for folding a molecule a few steps, but it takes you an awful long time, right? What we're doing now with our calculations is shortening those calculations by using an AI model of that, right? Takes 1,000 steps out of the calculation. We're doing this with the private companies because ultimately they will produce the commercial reactor. Right. Our job is to shorten the time for them.
Yeah, I think one comment on Steve's point there, because he's absolutely right. If we can curate, as I said, the fuse data and the simulation to create AI faster and faster models, you have two opportunities. One, I can look at faster, more scenarios, but two, that leads to disruption. Disruption, whether I want to apply that again in R&D or I want to apply that in terms of the way I make something through manufacturing. But those faster models that can run almost at real time or many times real time can then be deployed into the field for digital twin. And so this whole mastery of the computer science forum here in terms of mixing AI models and data is just going to be extremely disruptive in terms of speed, time, and risk reduction.
No, and it's an exciting time. I mean, we've seen, both in the Fusion Forward report that the SCSP just put out and the roadmap that we're releasing. I think there's a lot in there that talks about the convergence of AI, digital tools, and of course, our ability to be able to accelerate, research. And I think one exciting piece about this is really understanding ecosystems. Within DOE, of course, we've released the Fire Collaboratives, which is another ecosystem, another mechanism, if you will, of bringing national labs together with the private sector to really look at, not just R&D questions, but R&D questions that are well defined by the private sector. I think one aspect of this, of course, is relies on partnerships. And, of course, industry becomes a very important partnership. But another side of this is also the international partners. And I wonder, Steve, if you could maybe expand on this a little bit, because it's an exciting time right now, what's happening here in the United States, but it's all over the world, right? I mean, we've heard, of course, in the session just before the competition we have with China, but a lot of our relationships with our allies are really key on this question of accelerating R&D. Maybe you can expand a little bit on this, Sir Cowley, about
hey,
our great partners across the pond.
You guys fought a war 250 years ago, so you don't have to call me sir.
Yeah.
and so I'll now expand on why
Yeah,
Britain is such a wonderful place. The, Princeton and the UK have a real interest in trying to shrink the size and scale of fusion devices.
Yeah.
And so the spherical tokamak, which is the machine we're turning on next year, the UK has one. The collaboration between us is, hand in glove. Right? And they're very much interested in, we are stronger probably in the digital tools, right? And so we have a program right now to try and develop the digital twin of these devices, right? And that means integrating the engineering, how the neutron comes out, how it generates heat, how it breeds tritium, how from that you make electricity, and how you optimize that whole system, right? And I think, with our partners in Europe, in Japan, in Korea, we're doing work on the K-Star tokamak in Korea. We can move these things forward much, much faster.
Yeah, no, excellent. And Scott, here, and as we close out the session, these thoughts on what's emerging now for AI and digital tools, from your perspective, from Ansys' perspective, what's the next big thing? Where do you see this technology going? And of course, its convergence with fusion, where do you see that going?
I see maybe two things. First, I see an example, the ecosystem that you just described, where we're trying to do something that's really never been done before. We're partnering, obviously, with many of the labs in the United States, but with General Atomics and NVIDIA and University of San Diego, we're trying to build that digital twin capability. And what we're learning is that it does take an ecosystem. I mean, NVIDIA makes everything we do in Ansys in terms of simulation go faster, and we spend a lot of time with our new parent company, Synopsys, both American treasures, trying to make those chips run faster. But I would say the first frontier I see coming, model-based systems engineering, is absolutely going to change the way products are developed and serviced over their lifetime. We see today nuclear power plants being repowered for another 50 years. These were all born before the dawn of digital. So there was no historic data, no historic models to lean on. Agentic AI, I think in the short term, at a systems level of engineering, is going to help us do that, from understanding if I'm doing my work in the UK or if I'm doing my work in California. My work, my subsystem, my components can be wrapped in an agentic AI that can continuously be optimizing against somewhere else in the world's subsystem. And that could be in the supply chain, if we talk about ecosystems, or that could be at your customer operations. And I think that spans, that push into agentic AI to organize the work globally is going to change the way how we work and how we develop differently.
Yeah, fantastic. Well, thank you both for just a great chat here. And again, a lot of these, convergence of the AI and fusion energy development, a lot of these efforts is going to take great talent at the end of the day. And being able to be in a room here with all these amazing, talented, science and engineers, there's great hope that we're going to be able to get there. And so I just want to thank you both for a great conversation, and hope to see you again in another conversation like this in the future. Thanks to everybody for joining us in this session. Thank you very much.
Thanks a lot.